Now we can also translate the or use the equivalences that we had seen for sequences. So the limit when n goes to infinity of the sine of epsilon sub n is 0, where epsilon sub n is a sequence that fulfills this. Okay, it's a sequence that it has a limit 0, right? We also know that the limit when n goes to infinity of the cosine of epsilon sub n is 1, and this limits, right? The limit when n goes to infinity of the sine of epsilon sub n divided by epsilon sub n is 1, and the limit when n goes to infinity of 1 minus the cosine of epsilon sub n divided by epsilon sub n squared is 1/2. Okay, these things we know from our sequences, right? Well, we can use the definition of limits using sequences, right, to prove these limits. The limit when x goes to 0 of the sine of x is 0. The limit when x goes to 0 of the cosine of x is 1. The limit when x goes to 0 of the sine of x over x is 1. And the limit when x goes to 0 of 1 minus the cosine of x divided by x squared is 1/2. Okay? Now, with these limits and using trigonometric identities, you can have that the limit when x goes to a of the sine of x is the sine of a, and that the limit when x goes to a of the cosine of x is the cosine of a. So this is the actual proof that these two functions are continuous, which we'll see in the next unit, right? We can prove this from here, right? So let me erase this and, for instance, use the cosine, for instance. Okay, so we have the limit when x goes to a of the cosine of x, right? We can rewrite this because there's a limit when something goes to 0, okay? When the t goes to 0 of the cosine of a plus t, right? This is the same thing, right? A plus something that is going to 0, right? We can use the formula for the cosine of the double angle, right? So we have the cosine of a times the cosine of t minus the sine of a times the sine of t, right? Now this is equal to the cosine of a times the limit when when t goes to 0 of the cosine of t, but this is this limit, which is 1, and then this is minus the sine of a times the limit when t goes to 0 of the sine of t, which is 0. Okay, so the limit when x goes to a of the cosine of x is the cosine of a, right? You can do the same thing with the sine using this strategy, right? And the formula for the double angle, right? And similarly, we have our asymptotic comparisons for functions, right? So as just as we had when n goes to infinity, two functions behaved similarly. When we can have the same thing when x goes to a, and a doesn't have to be infinity, right? It could be any number, and so two functions will behave similarly. We say that they're asymptotically equivalent, right? So let f and g be two real functions that either both diverge or both converge to 0 as x goes to a, right? Well, we say that f and g are equivalent when x goes to a, and denote it like this. So this is the same symbol that we used before. X is similar to equivalent to g as x goes to a if this limit is true, right? So using this, we can rewrite the equivalences that we saw in unit 3 like this. So we have the logarithm of 1 plus x is asymptotically equivalent to e to the x minus 1, right? Which is asymptotically equivalent to the sine of x, which is asymptotically equivalent to the tangent of x, which is asymptotically equivalent to x when x goes to 0. Okay, that's important. When x is very small, these functions look the same, right? And as I've told you before, the idea behind this is that if you plot this function, right, and you get closer to 0, they all look like a line, right? So the logarithm looks like this. Okay, very close to 0. This is the logarithm of 1 plus x. Very close to 0. The exponential look like this, e to the x minus 1, and this is understandable because these two are inverse function. The sine of x looks like this. Okay, and around the line it looks very similar. Okay, all these functions look very similar to the line. Let me see, the tangent does something like this. Okay, around this is the tangent of x. Around 0 it does something like this. Okay, and then finally we have that 1 minus the cosine of x is asymptotically equivalent to x squared over 2, again when x goes to 0, and that means, as I told you, that 1 minus the cosine looks like a parabola when it's very close to 0. Okay, and yeah, so this asymptotic relationships that are very useful when computing limits, and in general to understand how these functions behave, we'll derive them in a more natural and systematic way when we get to Unit 8 on Taylor expansors, which is actually about how functions behave close to certain points. Okay, so that's the end of this video.